Okay, so yeah, so I've been thinking about the same type of stuff for quite a while now.
Yeah.
And a very dry way to say what it is it's separable algebras, but that's sort of a boring way to say what it is. So what it is seems to be some somewhat mysterious connection between two different subjects, both of which, as often studied, involve separable algebras, but one of which involves commutative separable algebras, and the other of which involves non-commutative ones, and in fact, sort of the most non-commutative ones, which are called central separable algebras, where the center of the algebra is as small as it can possibly be. So like if you're working with algebras over a field, it's just the field itself. And I guess I've talked about these two subjects before, but
Can I just ask you to remind me? So some of these separable algebras or separable monoids, depending on these, like you say, there's these two big separate branches of the theory, and you're interested in relationships between them. But remind me, is it on both sides of this division that we're thinking in terms of core objects, or is it just mainly on one side?
It's just on one side. It's just on the commutative. Sorry, it's just on the central side. So yeah, I'll list the two divisions, and I'll remind us which.
Okay, and core meaning this idea of taking the invertible stuff at multiple levels.
Right.
Okay.
Yeah. So, right. So,
I mean, have you thought? Have you tried to see if there is some core thing going on in the commutative case? I don't know. Anyway, sorry.
Yeah, there sort of is. Well, there's something going on. So,
okay.
So I think what I'll do is I will talk about the classical subject, meaning I'll be talking about separable algebras over a field. But ultimately, what I'd like to do, and I guess you already cottoned on to that, is replace the role of vector spaces here with objects in something like a general symmetric monoidal category. But I think for purposes of having some theorems already exist, I will talk about the classical, talk in terms of the classical case. So yeah, so then there are these two subjects. So one is the subject of commutative separable algebras. And then that subject often seems to go by the name of Grothendieck-Galois theory. And this is not the subject where this core concept tends to show up.
But boy, there sure as hell is homotopy theory lurking in the conceptual background.
Yes. So the idea here, if I had to like sum it up in one statement, is you can take like the commutative separable algebras over the field K. So they form a category with just algebra homomorphisms as the morphisms. And then the opposite of that turns out to be a topos, but more to the point, turns out to be some known thing, known topos. And so what you could say is you take So it's the category of continuous actions of this absolute Galois group of K on finite sets. So that's numero uno.
Yeah.
And there could be lots to say about that. But then I'll just dive straight into the second one. So the second subject is all about so-called central separable algebras over the field K again. And remember, that means they're algebras where the center of them is just the field. And again, there's a kind of theory about this. And so I guess if it has to have a name, you might call it like Brauer theory, or maybe probably more fair to call it like Brauer-Asa-Noether theory. And so what's the deal? So I guess they're like two, maybe if I'm stating big theorems, so there's like two theorems in this subject here. So first subject is the subject you're talking about. So if you take the core of this bicategory, where the objects are algebras over our field, the morphisms are bimodules, and then the two morphisms are bimodule homomorphisms. So that core there so its objects will be invertible algebras. So those are algebras that have an inverse with respect to tensor product of algebras, where inverse is defined in the way suitable to this context. So there's like an algebra A that has some inverse, and it turns out that its inverse is always the opposite algebra, and it's invertible if A tensor A op, where we're tensoring over the field K, is equivalent to the field K. That's the unit for the tensor product. And here equivalence in this bicategory here. So there's a bimodule between the two that's invertible up to a bimodule isomorphism. So this is called Morita equivalence, this notion of equivalence. So anyway, that's what they are. That's what the objects in the core are.
Yes.
But then the theorem is that objects in the core theorem. Objects in the core are just central separable algebras. So that's already worth thinking about. That is, why does it work? There's a fairly clean proof. I'm not quite ready to state, but it is really just a sort of bicategorical proof that doesn't require thinking about anything special about algebras over fields.
Yes.
That's very clean proof when you finally get to the bottom of it, although that's not at all how anyone started out.
Yes.
So that's theorem one, but then there's this other interesting theorem, which makes it even more exciting, which is that, so you can try to like determine what this more about what this core is like. So you can try to look at, well, so this core here is I guess it's like a 3 group. It has objects morphisms and 2 morphisms, and all of them you can tensor or compose, and they all have inverses. So you can form some groups out of it. You can form.
Sorry, and it's not or is a stable 3 group?
It is because.
Okay,
yes,
so it's a stable 3 group.
Yeah, because we're working over commutative ring here. So this tensor product is symmetric.
Yeah. Okay.
So,
Okay.
yeah, so it'll have 3. Well, I shouldn't clutter up the page, but it'll have 3 groups associated to it, which I will call pi 1, pi 2, and pi 3.
That was really a pi you were drawing?
Yeah.
Because it was like a K, and I was thinking, oh, that's interesting, calling it a K. But no, you're calling it
no. So pi 1 of this core, what it is it's like, so it's central separable algebras up to modulo Morita equivalence. That's one sort of grungy way to say what it is. It's just, but I mean, it's if you know what this pi 1 baloney is, it's it's just that. And so the theorem.
I have a question on this, but should I hold off or should I ask right now?
Let me just finish the sentence here.
Go ahead.
So this thing is, this group here is called the Brauer group of our field, as if there weren't already enough names for it. So that's what I mean by the Brauer group of the field. And then I just wanted to state theorem 2, which is that it's a theorem that sort of tells you what this Brauer group is in some other terms, which you can sometimes calculate. And it's the second cohomology of the Galois group, the absolute Galois group of K, with some coefficients. And these coefficients are, well, it's some invertible numbers with coefficients in some kind of invertible numbers. And what those invertible numbers are is that you look at the separable closure of K, which is, it's a big field that contains all the separable extensions of K, and it's almost like the algebraic closure. Sometimes it is the algebraic closure. But anyway, I don't want to sink into it, but let me finish this thing here. So it's coefficients in that. So yeah, I'll let you interrupt or not interrupt, but ask tons of questions. But the upshot of all this is like this.
Sorry, what did you say? What kind of cohomology? Did I miss what kind of cohomology that was?
Oh, group cohomology. So this is a group.
Okay, yeah, or yeah,
perhaps
profinite or something like that. Galois cohomology. Okay.
Let's see. Now you're trying to make it seem scarier, but it.
No, I'm not.
Okay, but I think I'm scared now that I think it's just cohomology in the usual sense of a group. Well, now I'm getting confused. Now you got me scared that like maybe we need.
No, but it's really, really close. I mean, Galois cohomology and, I mean, don't trust me on this, but Galois cohomology and group cohomology are almost synonyms, but it could be that, Galois cohomology is slightly adapted to the profinite case.
Well, that's what you're scaring me about. I thought I actually understood. this stuff, but now yeah, so there may be some tweak needed to deal with the fact that.
I think there might be a tweak needed, but I don't think it's scary, but okay.
Okay,
But
so now
I could, maybe you don't need it. Depending on how you do it, you might not need the tweak, but I don't.
So what was your thing you wanted to say?
Well, it's sort of a naive question. So it's sort of nosing around for interesting examples of this. So what I have in mind is something like I mean, your description of pi1 there looks like, yeah, and particularly if I allow the generality of, not necessarily separable algebras, but separable monoids. So, the sort of more abstract case. So your description of pi1 there looks like the kind of thing that in certain concrete-ish examples, I could imagine being some interesting, famous homotopy group. And I'm just sort of nosing around for examples like that. Well, I mean, part of the problem is that these, so these are three groups, so they just have three or something, a small number, 3 or 4 or something like that, interesting, or 2 or 3, perhaps 3 interesting homotopy groups.
Yep, 3.
And I'm not sure how much I've thought about famous, interesting homotopy types that are 3 types or something like that. I mean, you can get 3 types by truncating an n type for a higher n, but I mean, like I'm vaguely thinking of things like I don't know, buzzwords like Bott periodicity and Clifford algebras and stuff vaguely like that. I mean, this could be slightly off because, you've talked before about different ways that Clifford algebras do and or don't enter to this game or something like that. But, are there some famous concrete examples that we can shoehorn into this setup? Where concrete means, I don't know, something like, just famous homotopy types from some source, from, geometry or topology, or does the question make sense?
Yeah, it definitely does. So that's a great question. And
yeah.
I think that's great. So that's good. So I think I can give you an answer. So since it's a bit of a stretch, that is, it's a bit of it might blow up in my face, but I think it might not.
Sure.
But I think it's actually really worth it. So let me try it. So
okay.
So let's try doing. Well, let me start out abstract and then actually give you what you really wanted, which is an example. So So one of the peculiar things you mentioned is that we seem to be having this 3 type, a space that has just 3 non-trivial homotopy groups.
Yes.
Stable 3 type. And it is sort of hard to come up with examples of such things, and it's sort of much easier to come up with examples of just infinity types, just general spaces, and then maybe truncate them.
Yes.
And
truncate and or co-truncate them in some sense, but yes.
Yeah. So that's actually a good way to think about what's going on here, because I mean, so there's this weird thing that it's so far I haven't made any attempt to explain, is that this pi1 here
is
is H2, the second cohomology of some group.
Yeah.
And the reason why it's weird is because if you ask what about, I said we had a 3 type, so I had a pi1, a pi2, and a pi3.
Yes.
And it turns out that they're like very similar descriptions of pi2 and pi3. And they go like this. Pi2 is H1 of the Galois group. The same coefficients. And pi3 is H0 of the Galois group with the same coefficients. So I don't understand this nearly as well as I want. It obviously should have some very nice explanation. But what I'll do instead is I'll notice that, first of all, that this suggests that you should like keep on going, but it's going, but it's funny that it's like keep on going H1, sorry, H0, H1, H2, H3, H4, da, 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 da. But then here, of course, this is sort of like going down in this direction. So we're getting
Right. I often do get confused by that, but
yeah, I'm quite confused by it. But at least there is a type of entity where you allow yourself to go down into negative homotopy groups, and that's
sure. And there are dual spectrums.
Right.
And so very naively, I mean, what this notation and everything is suggesting is that, you know, as usual, there's something about humming one spectrum into another here, and you know, humming and you know, generalized cohomology is really about humming spectrum into spectrums or something like that.
I think that's right. And so I'm not going to try to straighten that all out now, although I want to more and more. But what I'm trying to do is I'm trying to answer your actual question.
Sure. Sorry. Go ahead.
It's okay. So your question was like, can we come up with an example of this? That is, can we come up with an example of some kind of space that's recognizable that gives us a Brauer group as its pi1? Maybe that's like one way to phrase the question. And so I'm going to say yes, but I'm going to sort of slowly lead up to it, I guess. So these cohomology groups, you can think of them as coming from a chain complex in the usual, or sorry, a co-chain complex in the usual way.
That's right.
And so that co-chain complex keeps on going.
Yeah.
And so you can sort of think of it like, it's a co-chain complex. So you can think of like 0 co-chains on, this is group cohomology. So on some group, so my group is this Galois group that I've been talking about, but I'm just going to call it G because I'm going to get sick of writing it. So we've got like 0 co-chains with coefficients in something. And then there's like 1 co-chains with coefficients in something. And so on. And this keeps on going on forever.
Yeah.
And so somehow this co-chain complex is going to give us, this co-chain complex is, okay, what is it? It's the cohomology complex for a group. But you can also think of it as the cohomology of a space. So the cohomology of this cohomology of this
Sure.
thing here. Yeah, in a very familiar way, the cohomology of this. I'm just writing to slow down my mouth. The cochain of this cohomology complex is the cohomology of the space BG.
Well, I mean, right, there is this thing which maybe to you is very annoying now, the idea that maybe this is a pro-homotopy type or something like that.
That, yep, you're right. It's a
Profinite version of a homotopy type or profinite version of a space or something like that. But
yeah, so for some reason or other in the example that I'm about to,
yeah,
I'm slowly working up to,
yeah,
somehow that seems like it's going to wind up being overkill. So I think part of the reason what's going on is what is all this profinite baloney. So sometimes very often you'll have like a field that has tons of field extensions, tons of Galois extensions.
yes,
Infinitely many different ones. And,
yes.
and so you sort of, each one of them is a finite extension, but you sort of want to study them all at once.
Yes.
And so that leads you into this profinite world. One way of dealing with all these.
I mean, are you hinting that you're going to use a prominent example of a Galois group that is just finite group?
Right. So I'm going to do a case where of a field that doesn't have lots of field extensions, so that this profinite thing just happens.
But it does have some
in a very really pushing the limits of the meaning of some. Can you guess which field I'm going to do?
Yeah, yes, it sounds like you're going to do the reals, and like this is very, yeah.
Yes. So I will not be a jerk and use some to mean one. I'll use some to mean two, which is perfectly fine. So so
but one of those two is a little bit fishy, but
fishy.
Well, it's degenerate. Degenerate extension.
Well, that always happens, but yeah.
Okay.
It's not my fault. So it's not the fault of the example that, yeah. So it's pushing the limits of triviality, but it's not trivial. So if you take K to be the reals, then the Galois group of the reals is Z mod 2.
Yes.
And then BG is actually very nice. I mean, it's very interesting, as you know.
Yes.
So Z mod 2 is RP infinity.
Yes.
And that has sort of interesting topology in some sense in infinitely many dimensions. Has just one homotopy group, but it's got lots of cohomology. So here the coefficients that I've never worked this out before, so it's fun. But so the coefficients we're using here, so this separable extension, the separable closure of R is C. That's the biggest, that's the only extension only non-trivial extension that we think of is just C, and so the coefficients for us is going to be the invertible complex numbers. Now, let's see. I don't even know. This is sort of embarrassing. I'm not even sure I know instantly what the cohomology of RP infinity with these particular coefficients is, but I think I know what it is. All these kind of cohomologies of RP infinity, they're going to be periodic with period 2. That's just sort of how they work. And then like the thing you have to like straighten out in your mind is is what is it exactly? So that's a question anyway. So the question is like, what's the cohomology of RP infinity with coefficients in the invertible complex numbers?
Sorry, is this when you were when you're describing these Galois cohomology or group cohomology descriptions, definitions, did you I wasn't thinking about the action of the group on the coefficients. Was there any interesting action?
Wow, I'm so ignorant. I bet there must be. Yeah, there is. So yeah. So the Galois group definitely acts on the separable closure or algebraic closure. It's just, that's the main thing it acts on. And that's the thing that the Galois group is born to act on. And so you're right. So I'm never going to really figure this out carefully right on the first fly, but these are definitely with non-trivial twisted coefficients. Good point. Thanks for. So ZMod2 acts on C star but shouldn't
there be some evident or semi-evident geometric interpretation of the action here? Am I missing? I mean, maybe at some point we should go back to where you wrote the three of them. The three definitions.
I think in this, what I'm going to try to do is I'm going to try to use my other knowledge of what these three different groups are.
Okay. Yeah.
In the case of the reals, to know what these.
Now that I see your definitions written in here, just the way the letter K is appearing is very, it sort of suggests like there's some evident Einstein pairing interpretation of what the action is.
What's an Einstein?
Is that the Einstein index convention? What do you call that? I mean, just like the variable is appearing twice, and that must be just the way the variable K is appearing twice. The letter K is appearing twice. That must be telling us how the Galois group is acting.
I guess. So I mean, the way I don't know.
Or is it? Let's see. Or is it trivial? Let's see.
Well, there are two possibilities that are standout possibilities, which that it acts trivially, or that it acts in the way that the Galois group was born to act on the separable closure. Sorry to keep saying.
So yeah, maybe it is.
And that the latter one is, I think, the correct one. Actually, I think I happen to know, because I sort of know why this stuff is true vaguely. So I think it is acting in a non-trivial way. So in our example, that non-trivial way is that ZMod2 acts on C star by sort of complex conjugation.
But wait. Can you go back? So I thought you were talking about the case where K is the reals.
Yeah.
But then I thought you said we're taking the multiplicative group of the complexes.
So that's the separable closure.
Okay. I missed the letter S there. Okay. Yeah. Okay. So right. So that is Texas. So just the functoriality. Right? Doesn't that make sense? Yeah. Okay. So it's just the act. Yes. What you said, the way it was born to act. That's what I meant by the Einstein convention.
Okay. Yeah, that is the way. So
okay, so the right, that is a group of automorphisms of KS. And so, yes, so
Right.
it is that. Okay, I was just catching up to obvious stuff here. Okay, so there's a very evident action there.
Yeah,
Okay. Again, I'm just kind of catching up here. Okay,
no, it's fine, because
Yeah.
I think I temporarily completely forgotten about that. So
Yeah,
that like
yeah.
reduces the chance that I will by any principled method just like calculate this cohomology on the spur of the
Right.
moment.
Right.
Because I actually sort of probably do know how to calculate various cohomologies of RP infinity with various untwisted coefficients, but here we
Right.
need twisted coefficients.
Right.
So what I will do is so what I'm going to do is like a real cheapo method, which is, so which might not even be correct, which is that, so lots of different cohomologies of RP infinity, like with different kinds of coefficients, are periodic with period 2. So that's true for the untwisted coefficients. So I'm gonna just like hope that that's true here. But what I
Yeah.
but what I know anyway is I think I know what these 3 cohomologies just actually are.
Okay. Okay.
So well, that'll actually even give me one check of whether it's periodic period 2, because
Sure.
these two better be the
Sure.
same, and maybe it'll turn out to be false.
Right.
So okay, so let's see here. So here's this cohomology. So well, so H. So this I'm getting get sick of writing that. So I'm just got HI. So just to remind ourselves, so H2 is this one that's supposed to be the Brauer group. Yeah, I mean, that's a theorem that it is the Brauer group of our field. So this is going to be the Brauer group of R.
Yes.
And so they're just 2 central simple algebras over R up to Rita equivalence. And those are the reals and the quaternions.
Yes.
And then so we get Z mod 2 for that one.
Yes. I think I'm following. Yes. Sort of.
And then let's see, the others I haven't thought about so much. You'll have to help me out here. So
Sure.
the first one. So that's, wow, I may really bomb this, but that one is the invertible
Picard.
with the bimodules, and it's called the Picard. That turns out it's called the Picard group. Yeah, so this is the. It takes a while to figure this out, but I think it winds up being the same as the.
Say again, the invertible modules of what?
Well, of R.
Well, those are easy. I mean, those are right
Yeah.
for any field. It's just going to be trivial, right?
Yeah. So I think this one is trivial. That's right? My best,
Yeah.
That's my best guess. Yeah, that's what I'm coming up with.
Okay.
Yeah, but that is, if it is just the invertible, there's some little nuance here, which is that, which was not so little, which is that this core business was about not really about modules, it was really about bimodules. So what this thing really is it's our bimodules up to isomorphism. So these are like isomorphism classes of R bimodules, and the way it's becoming a group of invertible, of invertible R bimodules. So the way it becomes a group is by tensoring. You can tensor 2 R bimodules and get another R bimodule.
Yeah, but that still seems very trivial, right?
I think it is. I think it is trivial. Yeah, it's trivial.
Okay.
So okay,
but sorry, is it? But But
It's
is
just one, but for people who are like listening to us, there's just one of these things. It's just R itself as an R bimodule.
But are we in danger here? Are we saying that it's always trivial for any field? Again, I mean, that's right.
We are in danger, but I think it's true. I think I get a little confused about this, but in some number theory cases,
yeah,
extremely interesting. We use not the field, but some ring of algebraic numbers, and then all of a sudden it becomes quite interesting.
Right.
It's the, what do you call it? The class group.
Right. It's just, but you made it sound like, the classical case was the field case, several algebras over a field. And now it sounds like we're saying in that case, the Picard.
Yeah. Yeah. So in some kind of classical case uses the number is the study.
I mean, again, am I making a stupid mistake here? Am I using the wrong tensor product of these bimodules? Let's see. I'm not quite sure, but for this example, I'm willing to go
I think it's trivial, and I think like some of the stuff you're alluding to has to do with the fact that we might study this whole subject where we start out not working with a field, but like a really classical case would be to use a number ring to get this bicategory and take its core. But it turns out that like when you calculate the Brauer group and so on, you still get into Galois theory, but it's like Galois theory for the field associated to the number ring. So it's like the usual thing that you're always complaining about, which is like sometimes it's sort of hard to tell when you're somehow like the number ring and its associated field of fractions are like joined at the hip, so that sometimes you almost can't tell like which one you're really talking about.
Right. There are a lot of
So I think that happens here. But right now I'm just talking about this field, I guess. So although I'm nervous that there's like, but anyway, I think for the case of the reals, there's really no there's no way out of what our conclusion here. I think that's right. And so then H0, what the hell is that? That would be the this is interesting. That would be the, so that would be like the, that'd be like the isomorphisms, sorry, the automorphisms of R. The automorphisms of the identity are R bimodule. So it's the automorphisms of R thought of as an RR bimodule. I think that's what that works out to be. Automorphism group of R as an RR bimodule. And so I think that what we're getting, so it's not working out quite the way, not quite working out quite the way I was.
Well, can I think for a moment? Can I
sure. Yeah, please. Yeah, I would let you should. I'll give it as a puzzle here. So
these RR bimodules, I can think of them as endofunctors. I think I can get away with thinking of them as endofunctors of the category of real vector spaces.
That's good. Yes, you can. Probably to be super persnickety, they'd be like endo linear k-linear functors of the
yes the reasonable nice endofunctors here. And then now you're just asking for auto equivalences of that functor.
Auto, yeah, uh-huh.
Is that right? Auto equivalences of
Auto natural isomorphisms of that
that
function, yeah. Uh-huh.
endo functor or that auto functor. So these are natural. Mike, totally scrap here. What are these natural? Am I totally scrap here? Natural ways of assigning to each. Natural way, natural.
Sorry, do you want me to say it, or you're all sounds? I want you to say it. You're almost saying it, but you're like fizzling out.
I mean, now it sounds like you're saying it's the multiplicative group of the reals.
Yeah, it's the multiplicative. There are natural ways of assigning to each real vector space a
DL1
transformation.
R, also known as the multiplicative group, yeah.
Yeah, so this is always the units group of your, like we could do this very generally for any field or any ring, and you just get the units.
Okay.
So this is our star. So it's interesting that we're not getting that it's periodic, but we're sort of getting that it's like morally periodic, because in homotopy theory, our star is sort of like Z-mod 2. It has two connected components. I don't know quite what that.
So there's a homomorphism there. Yeah.
I don't know quite what that
means.
What that really winds up meaning, why this and this Z-mod 2. It's sort of like it should be Z-mod 2, but we haven't like modded out by enough stuff or something. But
can you go back for? Oh, were you going to say something else? Go ahead.
Yeah, no. So this is an example. This is an example. So
yes,
this is a good example of a concrete. Yeah, and I should work it out. So what were we going to say? Should I want to go back somewhere?
Yeah, go back a couple of pages here.
Oh, I managed to erase a page, which is very upsetting.
Oh,
just in the flick of a switch. One page went away. I can't make it come back, but so I can do this page here.
Okay, this page here. So this page here. So let's just go back for a moment to a moment when maybe one or the other of us tricked us both into forgetting about the twistedness of the coefficients. And when I was in that frame of mind, I was thinking that this is cohomology. Again, this is just humming one spectrum into another, but in a very restricted way. I mean, what am I trying to say? That I haven't thought about a lot of this in a long time, but if that were true, that would sort of be telling us that I think that would be telling us that, the situation is too trivial for there to be any interesting Postnikov invariance between homotopy groups of the core. Whereas, are there in fact interesting, in general, maybe in general, we are expecting some interesting.
So I asked that question on Math Overflow once, and I think I asked it for the case of a commutative ring.
Yeah.
Any commutative ring.
Yeah.
And Jacob Lurie answered it, and he said, no, they're just trivial Postnikov invariants.
They're all trivial for a commutative ring.
Yeah, and I'm still a little puzzled by some aspects of his answer, but it definitely had to do with the fact that he was claiming that the relevant homotopy type is actually the homotopy type associated to a chain complex.
Right.
Which I think is this cochain complex.
Yeah, I mean, my argument in the case of the untwisted coefficients was even simpler than that. But maybe now you're saying that it's just a chain complex.
I mean,
I think that's right. I mean, I have to check the little make sure I didn't fall for a level set there or something like that. But yeah, that sounds like I think I'll have to check the details, but that sounds like a reasonable argument that in fact there are no.
Yeah, I mean, the argument is a little harder than that because we had this homotopy 3 type that we had defined in terms of the core.
Yeah.
And then, I mean, so here's like a bogus argument. Bogus argument is like, you have that homotopy 3 type.
Yeah.
You want to know its homotopy groups, and then you show that its homotopy groups are the same as these cohomology groups. And then you say, hey, those cohomology groups come from a chain complex or a cochain complex. And for a chain complex, you get a space.
Right. You do have to be careful there. It does depend on the homology dimension of the ring. Right. I mean, am I saying this wrong?
Well, I was just going to say a different problem, which is just that, like, merely having shown that the homotopy groups of some space match the cohomology groups, or let's say homology groups of some chain complex, doesn't mean that your space is the space that corresponds to that chain complex. It could be that, like, you somehow squeezed out the Postnikov invariance when you created this chain complex. So there's like, you have to like think harder to see, like, why is your space really, why is it really the chain complex? That's all I
I'll have to think about that, but there's a bunch of vague questions in my mind at this point, but I shouldn't really ask them right now. All right, so where are we now?
Maybe we should stop.
Well,
maybe we should.
But are we in the middle of a digression, or did I
didn't have
you, or go ahead.
I didn't have a huge fixed agenda. I will just pose the question that's like the question that I always pose to myself. Yeah. So the question is, which I've posed to you before, is like, so what's going on here? Okay, so we've got these commutative separable algebras.
Yes.
They're very closely connected to actions of the Galois group on finite sets.
Yes.
And we should really think of this as like some version of covering space theory for covering spaces of BG, where G is the Galois group, something like that. Maybe here we have to worry about the profinite. We do have to worry about the profiniteness here. So there's that. Anyway, so there's that thing that has a nice appealing geometric interpretation of it. And then we have this other story. I think maybe I didn't erase anything in the end. I just created a blank page. So story 2, these non-commutative central separable algebras, and studying them. They show up when we're studying this bicategory associated to our field, and then it too turns out to be connected to the Galois group.
Yes.
And it turns out to be sort of, in its classical version, it's sort of like a 3-part. It's part of a 3-decker story about 3 different cohomology groups of BG.
Yes.
But it's a story that really could go on to higher cohomologies of the Galois group.
Yes.
So sort of the question is sort of like, how are those fitting together? The first is about covering spaces of the Galois of BG. And so you just sort of only need to know about pi1 acting on sets. The second story here is sort of a linearized story where you're looking at cohomology of BG. And what does the cohomology of BG classifying? Well, you can really think of H1 of BG with coefficients and some invertible things. You would often think of that as being connected to line bundles of some sort.
Yes.
So in some sense, some vague hand wavy sense that could be made.
Sure.
This is about like line bundles. Line bundles are sort of in the same ballpark as covering spaces. Covering spaces are like set bundles, and these are like line bundles. But for some reason or other, the central separable algebras are actually like talking about not H1, they're talking about H2. And those are some kind of subtler, that's classifying some subtler things over BG.
Which you've hinted at.
Yeah, which I've called gerbs.
Yeah.
Or if you're thinking very geometrically, like sometimes those are just, you think of those as bundles of algebras, bundles of matrix algebras over a space. I mean, if your BG was a God honest to goodness space, H2 of BG with coefficients and invertible elements of some field, I don't classify in a certain way some equivalence classes of algebra bundles over that space. So there's definitely they're fitting together in a certain way, but it's a somewhat funny way. Yeah. And it's also sort of funny that, I mean, it's funny that the first story is sort of about pi1 and the second story is about H2, but they're both about separable algebras. And the second story, because it involves cohomology, it's sort of begging to go on up to higher cohomology groups.
Yeah.
Whereas the first story, since it's just about pi1 of BG, it's not so easy to make that go up to higher dimensions unless you do something fancy that replaces the Galois group by some kind of higher group. So getting them to fit together in a nice way is, it's bugging me.
But they're, it's, it's a reasonable, general, vague question.
Yeah.
How
okay.
How do
they fit together?
How to try to mesh these things together? How to try to relate them together? Yeah.
Yeah. So that's basically what I'm on.
Okay.
That's the story.
Okay.
So thanks for making me do an example.
Okay.
I will actually sometime try to think about these twisted. So there's supposed to be like a twisted circle bundle or C-star bundle over RP infinity, where the circle sort of gets like reflected somehow as you like go around the non-contractible loop. That's a sort of should be fun.
Sorry, say that once again. You're supposed to what?
So,
I mean, can you just say it the way you said? Go ahead.
Okay, there must be some circle bundle.
Circle bundle. Oh, circle.
Yeah, bundle. So I'm taking my C-star bundle and doing homotopy theory. Just think of that as like a circle bundle. That there's a circle inside the C-star.
Okay.
So there should be some like twisted circle, non-trivial circle bundle over RP infinity, which has the property that when you carry the circle around the non-contractible loop in RP infinity, the circle gets reflected. That's the action of the Galois group that's the action of the Zima2 on C-star. It's a reflection.
Yeah.
So we're sort of thinking there's some kind of geometrical picture of what we're doing here that I haven't really thought about.
Okay. Oh yeah, I'll have to think about that.
Okay.
So we're gonna
maybe I should pause it. Yeah, I'll pause it and
prepare
for the second act.
Okay.
Let's see. Okay.
Okay, so I'm really going to try to ask you some questions, try to get you to help me to figure out some calculations and things here, which is maybe what I always try to do. But the things I halfway understand here, I'm trying to get you to help me to fully understand them. So, and it's certainly following up on stuff we've been talking about our reciprocity theorem and things like that. So let me start drawing an example here, and then we'll try to figure out what I'm trying to do. So let's take the Gaussian field, which I'm notating as the Gaussian rationals, but the Gaussian flavor of rationals. And now I've got an extension of that, which is going to be the Gaussian rationals adjoin two generators, two variables, two unknowns, whatever we call them, and modulo some relators, and it's going to say it's going to say that A plus B times W cubed is going to be equal to, well, it's a specific strange number. Maybe I'll just call it K for now, but K is actually a particular constant. Let me write up here at the top. So what is it? It's K equals, let's see. I'm hoping this is not going to dissolve into a just complete mass of impenetrable calculations. So there's a good reason why K is what it is, but let me write down what it is. It's equal to -1 plus 5i plus -2 minus 3i times W. Okay, but that whole thing is multiplied times 1 plus 2i plus 2w. Now,
you're going to remind me what problem we're solving that led us into the jaws of this constant.
Yes, we are trying to understand Z mod 3 torsors over the Gaussian field. And I'm trying to draw one of those. So it involves taking a cube root of a certain quantity, but this quantity is sort of a formal quantity. It's not, it's actually like, so, there's this mysterious W that has been showing up here, which we haven't really said what it is, but so W behaves formally like our favorite primitive cube root of unity. Now, this terminology behaves formally here. That's concealing a whole interesting big story about how about like exponentiation of it's sort of like an analog of the kind of categorified exponentiation that happens in the sort of synthetic differential geometry, where you have this infinitesimal space, which is the walking tangent vector that you use as an exponent, and you take, and you turn the tangent bundle into an exponential in that way. But here I'm not doing it to the walking to the walking tangent vector, but I'm doing it to some other. I'm doing it actually to these fields, like the Gaussian field and the Eisenstein field, particularly the Eisenstein field, as an extension of the rational field. So I mean, yeah, there's a number of highbrow stories about what we mean when we say that this behaves formally like 1 to the 1/3, but I'm going to try to deal with that somewhat intuitively at the moment. So, and I hope that's something. Yeah. Okay.
Yeah.
So, and I wrote my relator in quotation marks, meaning that you're supposed to interpret it formally. What W is not actually involved here. It's just, the coefficients of 1 and W. So right, it's like we're sort of dealing with formal power series in this variable W, but because W behaves formally like 1 to the 1/3, which means that W squared plus W plus 1 equals 0. It behaves formally like that. That means that these formal power series are very truncated. All they have is the constant coefficient and the linear coefficient. And so this.
Yeah. And so so the particular K you're getting was because you were wanting a particular
yes.
Z mod 3 torsor that had, gosh, it's amazing how much I've forgotten since last time. So you
it's such a ridiculous story that it's hard to remember the details, but go ahead. Yes. It's going to get a better story as we go along, but yes, go ahead.
But you were you drew some pictures of some finite sized patch of the Gaussian integers.
Yes.
Can you remind me what?
Well, so I mean, right, we're aiming to have we're aiming to have an extension of the Gaussian field that has a particular splitting pattern. And it sounds like you're talking about our attempts to draw this splitting pattern. And let's see. So
if you don't want to get into that, it's fine. But
well, I think the one that I'm really aiming for is this splitting pattern that will have a density of 1/3, and it will be something. It would be like it'd be like, for a Gaussian prime P, we want P to be congruent modulo 2 plus 3i to either 1 or I or -1 or -I. So this is a splitting pattern, and I think it looks like, so what does it look like? It looks like something like, let's see, don't tell me, what is it, 2 plus 3i? So it's like up there and over there, down there. Okay, this is the zeros of this, this is the ideal, the things that go to 0 on this quotient, right? Et cetera, et cetera, et cetera. But the congruence class is where the primes are supposed to live. It's supposed to be, right around that, the 1 and I and -1 and -I. So it's supposed to be a splitting pattern that looks like this. So it's got these sort of diamond shapes. So the norm of 2 plus 3i is 13. Right, so what is it? 2 squared plus 3 squared equals 13. So the so-called norm of this Gaussian prime 2 plus 3i equals 13. So you take away the 1, 0 element, that gives you 12, and then 12 over 4 is equal to 3. So we've got to split, or 4 over 12 is equal to 1/3. So we've got a splitting pattern of density 1/3 here, basically, in the multiplicative group. And I'm trying to reverse engineer a particular abelian cubic extension of the Gaussian integers that will exhibit this splitting pattern. That the Gaussian primes that split will be exactly the ones in this red pattern here. And so we went through some, bizarre process here to cook up this K. And it involves taking 2 plus 3i and factorizing it over the Eisenstein integers. And then there's, and then there's even further gains. But this is all attempting in a somewhat Rube Goldberg way, or what is it, Heath Robinson? That's the British Rube Goldberg. In a Rube Goldberg way to cook up this torsor, this abelian extension, abelian cubic extension, which will exhibit this splitting pattern, and that's the goal. But okay, that sort of attempted to answer your question.
Yeah.
I'm attempting to create this torsor. So I'm trying to get this to be a cubic extension, for one thing. I'm not even sure I'm succeeding in that yet, but we're going to try to get a cubic extension, and then this cubic extension is supposed to have an order 3 endomorphism, maybe I'll call it, I don't know, C. Which is going, right? I mean, so this is going to make it like into a torsor. We have many different ways of thinking about these torsors, these Z mod 3 torsors, these abelian cubic extensions. And I'm as usual, I'm mixing together these very highbrow ways and these very lowbrow ways of thinking of it, and getting myself into trouble in this way. And that's the trouble you're supposed to help to try to get me out of.
Okay.
But right, I mean, so we have this algebra geometry duality. So we're having the torsor is like a bundle. So here's the base space, and here's the.
I don't see what you're pointing to.
What? You can't see the cursor?
Huh?
You can't see the cursor here that I'm pointing to?
No.
All right, then I'll just like circle it and then erase it or something like that. So this is the base space over here, and this is the total space.
Mm-hmm.
But the arrows are reversed because we're looking at the algebraic picture.
Yeah.
So algebraically it's an extension, but geometrically it's a bundle. And it's supposed to be a bundle where the fibers are supposed to be of size 3. And not only are the fibers of size 3, but there's this orientation on them. So this C here is sort of like the orientation thing that makes this actually into an abelian. Right? Because that's right.
Mm-hmm.
If you have this bundle, this covering space where the fibers are size 3, and you have this natural or this continuous orientation action, then that's actually making it into an abelian, because it's cutting the what do you call that? The deck transformation group or something. It's cutting that group down to 3 elements. To to the Z mod 3.
Mhm.
So so that's what I'm trying to do here. That's what I'm trying to do here.
Uh-huh.
And but I'm not sure I've actually written down the correct thing here. I think it may be that I may have forgotten an extra relation that we might need to write down or something like that. And because when I asked Mathematica to solve this system of equations over some finite fields, or I think what happened was that I ended up getting 9 solutions, and I was expecting 3 solutions. So you see what I'm saying? I have a feeling I didn't quite do it correctly, and you're supposed to try to help me figure out the right way to do it here. So, right, I mean, right, I was expecting fibers of size 3, and if I interpreted my program correctly, it was telling me I actually have a fiber of size 9, which means I didn't quite write down the correct thing yet. So, so this is what we're struggling to try to figure out here. So you know, I don't think it's actually going to be as bad as I'm making it sound, but let's go ahead and see
Uh-huh.
how this
Okay.
works out. So, so the key thing is that by Galois descent, when we tensor this whole thing with the Eisenstein field, the Eisenstein rationals, then it should, you know, split in and work itself out into a much more recognizable form. So let me try to write that. Let me try to write that down. So let's see. So what's going on here? So let's see. Maybe I can. I'll try this. See if I can do this. How do you do this? You're supposed to. Sorry. You know, let's see if I get myself in trouble with the understanding how the editing works here. Let's see. So I'm supposed to sort of circle that here. And I click on something, copy. Okay, and then I go down here. Let's see, maybe I go down here.
Sounds good.
One of these days I should really learn how to do this stuff, but
Good.
okay. So like I said, I'm supposed to tensor this whole thing with the Eisenstein rationals. So we're going to have what now? We're going to have.
When you tensor it with the Eisenstein rationals, does the
Yeah.
formal W turn into the actual W?
that's sort of morally yes, but we've got to figure out what that really means. Yeah, it's something like that.
Okay.
I wish it would. Yes, we're trying to get that to make sense somehow. So let's see. So we're trying to say that well, okay, so you know, we're just going to tensor everything here with, well, I guess I'll write it down. So we're going to have this. And I guess okay, so that whole thing, and then I join A and B, and right, I guess at this point it's still formal, but we're going to try to get it to be actual or something like that.
Sounds like Pinocchio trying to become a real boy or something.
Yes, it's that sort of thing. So
Just tensor him with a boy and something.
something like that. Let's see. I mean, right, that is the ideal that we're aiming for in mathematics. You want things to happen magically. Like, you know, you have to be able to just say what you want and get it.
Exactly.
And you know, I'm not quite at that point yet, but
like you wave your wand and hope it works, and it doesn't always.
Right. So let's see. So, all right. So,
Can you remind me what
Yeah.
QG tensor Q is? It's a field, right? In this case.
it turns out to be the 12th cyclotomic field because
Okay, good. That's what I was.
you're adding the 4th roots of unity and you're adding the 6th roots of unity,
right.
and the least common multiple of that is the 12th. 12. So it's 12th roots of unity.
Yeah. Dolan.
But it's it's a degree 4 extension of the rationals, and you can think of it in many ways. But
Good.
right. So so let's maybe I'll try to write some of this more explicitly. So let's see. This thing up here is Q adjoin I modulo I squared plus 1. So that's just a way of writing out what the Gaussian rationals really is.
Yeah.
Did I do that right? Except maybe the dot over the I. Okay, and so this thing over here is Q adjoin I and A and B and modulo I squared plus 1 and modulo this formal thing. So W cubed equals K. Yeah, I think it really is true that for almost all the purposes of the questions I want to ask you, we're treating K as a black box here, right? K was that ridiculous mixed Gaussian and Eisenstein number that we wrote at the top, but I don't think we need to open up that horrible black box for the questions that I'm trying to ask you.
Okay, good.
So yeah, so I think it's like that, things like that. And so, but now we're tensioning with the Eisenstein rational, so that just means that we're throwing this W into the mix as well, this actual W. So what do we have? We have I and W and no, yeah, right. This is just I and W. Okay, so where is this? This is like here.
Are you gonna call the actual W the same thing as the formal W?
I am. You think that's what's getting me in trouble?
Don't do that. Yeah, please don't do that, because it's sort of like a sleight of hand. And I'd like to see how it actually works. And you're gonna.
I thought it would be okay because of the fact that I mean that is the kind of thing that we're trying to. What am I saying? We're trying to streamline the way that you actually. W only appears inside of quotation marks here, so that's the thing that is supposed to make it okay.
I would be really happy if you could use a different kind of W for a little while until we see how it how it works. Because anyway, I'm worried about it.
All right, but
so if you could call that
I'm disagreeing about that being the source of the confusion. But let's see. So what I'm hard for me to think of good letters here.
How about V?
All right, okay, we'll use V. Okay. V. And then A plus B W cubed equals K. Sorry, I meant to. I'm right.
Yeah, you got a little
carried
away. If you're just doing the left-hand one, you don't want that last.
Right. Okay. Let me just.
Yeah.
Okay, so would you want that? Okay, so okay, and then okay. So it's Q I V. Yeah, I think it would work so much better if we did use consistent, just called it V and W. Right, so we should have called one of them U and one of them V. And then, I could think in like the Roman alphabet, or you could think in the English alphabet or something like that. Let's see. Because the Romans didn't distinguish U from V, but let's see. I think. So this is where A and B come in, okay. And then we have I squared plus 1 and V squared plus V plus 1 and A plus B times W cubed equals K, but only interpreted formal. Okay, but what I want this to be, so what am I trying to say? I want it to be like what I'm really aiming for when we get by the Galois descent is let me see if I can write it down over here. So we have the same thing over here. I and V and that stuff. And then here we have I and V and just something I'll call X. And we have X cubed actually is equal to K. Well, this is why you really want to use V and W the same, because this K here means the actual K.
Oh, okay.
Right. K had W in it. If you look at it was. So it's but
right. Yeah. Now I'm wanting. Anyway, now I'm wanting you to use like some kind of bar to mean actual or maybe bar to mean non-actual, and then you could
what I'm using is that, and maybe you're not happy with this, but my idea was that putting things in quotes means it's being used
I can
formally or something like that. Yeah.
Okay. Yeah. Yeah.
I should try and get away with that for now.
Well, I think so. Yeah. So.
Okay, those are W's, and that's a W.
Okay, so if you really needed to, you could write just W in quotes.
Yeah.
Thing in itself.
Well, maybe, but but really the quotes should be around, right? Because this relator is really a pair of relators.
Right. Yeah. Okay. So. Okay. Well, anyway, but you have now it's your job. Well, you don't have to accept it, but it's your job to convince me that those two are the same.
Well, I think they can't be the same, and they're grossly not the same. Maybe, but let's try to get some homomorphisms going in some directions here. So let's see. Right, I think we want to say is the the obvious thing here maybe is that.
Can you let's see. Can you change that V in the top one there back into a W since you decided you're not going to?
Yes, sorry.
So you got a W there.
I hope I got rid of all the V's and put into W.
True W, and then you've got this relator that has a fake W in it.
Yes.
Okay. So we can map the real W to the real I to the real I, the imaginary I, the real I to the real I, the W to the W.
Yes, and the only thing we have to worry about is the X, and that simply goes to A plus B times W.
Okay, what is that? And that's okay. And it doesn't even make sense to say A plus BW in quotes.
That's right. That's right. That's right.
You couldn't map it to that.
That's
not a thing. Yeah. Okay, I get your.
That's right. Right. But okay, but then there is some, right? There's some sort of magic here that you have to check that the fact that X satisfies this thing is supposed to mean that, right? I mean, we want to make sure that this relator is getting preserved here, and hopefully we can observe that this is, if I did it right, that this relator is getting preserved. That this is a homomorphism.
Okay, well, I guess that's maybe a way to see my question coming up. That
Yeah.
So somehow, for some reason, the fact that you put the relation in quotes holding is gonna imply that the relation without quotes holds, right? For this to be a homomorphism, you need A plus BW cubed equals K to be true.
Yes.
Without quotes.
That's right.
And so you have to somehow get that from the fact that A plus BW cubed equals
right.
K.
And I was hoping that would just be some nice, easy Pinocchio-ish thing. But we want that to happen. It wants it to happen, and it does happen.
I don't think you can just like.
Well, I mean,
like
okay. So you're worried about if this is really.
I mean, there should be a way to see why it actually happens, not why we want it.
Sure. But let me emphasize something here. I'm suggesting that this is not going to be the hard part, and I want to highlight what I think is going to be the hard part, and in fact the impossible part, because I think I didn't put in enough relators or something like that. So the hard part is when we try to have the inverse homomorphism going backwards.
Mm-hmm.
And for the inverse homomorphism, so basically, for this direct homomorphism going in the upwards direction, I have X is basically just the Gaussian quantity that the Eisenstein quantity that you form from, coefficients A and B. But to go backwards, it's more like I want to say, A should be the constant coefficient of X, whereas B should be the W component of X. But that doesn't seem to have any obvious meaning yet. So I think that might mean that I need some more relators up here or something like that. And maybe what am I trying to say? Could it be something like that?
More relators
on the top. That what am I trying to say? That does it make sense to be like a
I just will make a wild guess. I will make a wild guess. So you're saying like I'm gonna guess that you also need more relators on top to get the map going up to really be a homomorphism, to really define a homomorphism.
That could be, but I didn't.
So right now we're in the situation is that like we're hoping that like the upwards map is a homomorphism. At least you can, even if you don't know that, at least you have like a candidate. The downwards map you don't even have a candidate for until because you don't know what A and B should go to separately. And so your idea is that you're going to stick in a relator on top so that the downwards map, so that we know what the downwards map, so that we have a candidate for the downwards map. But I'm just going to wildly guess that I don't know if this is true, but I'm just going to guess that we also need that same relator to get the upwards map to be a well-defined homomorphism.
All right, let me think about that, because I could be making a mistake, but well, first of all, let me just say my vague idea for the conceptual meaning of these extra relators. And I also already said something about that. It's in some sense it's supposed to be vaguely some sort of Galois descent relator or something like that. But no, what do I mean by that? Well, I mean that. What am I trying to say? So, well, first of all, the thing on the bottom is supposed to be manifestly or almost manifestly a Z mod 3 towards over this, combined thing of the Gaussian and Eisenstein. And it looks like it's kind of manifestly a Z mod 3 towards because I mean, right, we're just taking a cubic polynomial, this x cubed minus k. And it's sort of supposed to be obviously abelian because the thing that's going like this is just supposed to be,
X maps to omega, sorry, to W times X.
Yes. X goes to omega.
You said omega.
Right. Well, right. I'm trying for these purposes. I'm trying to get us to think that omega and W and V are all the same thing.
Okay, just like Z and Z.
Z and Z. What are Z and Z? Yes. Okay, that's true. Yes, I think that's correct.
Omega is just like a weird way to pronounce W.
That's right. That's right.
Okay. Yeah, that I buy. And then you're saying that but you're not getting it on top. You're not getting that in the automorphism.
Right, but I clearly want it to be, right? I want, right? I mean, I want this thing that when you, well, have I made it completely clear why I want this? But I do want this. I want, right, a Z mod 3 torsor, when you pull it back along this cover or push it forward along this co-cover, it should give you another Z mod 3 torsor, but one that is perhaps more trivial or more manifest or something like that. So, I have good reasons for thinking that this is the one I want when I pull back along this cover. This one on the bottom is the one that I want to get. So that means that if that's the one I want to get, then I better, make sure that this thing on the top really is agreeing with it. Am I saying that right? Let's see. So right, because the thing on the top is obtained by pulling back along the cover. Right, that's how we got this thing on top, is by pulling back. But it may be that the thing that I pulled back along the cover may have been slightly the wrong thing. So right, you see what I'm saying? The extra relators that were supposed to be in there didn't involve W at all.
Sorry, what's the cover?
The cover is the the cover that you get by pulling back along the spectrum of the Eisenstein field. So we're tensoring with the Eisenstein field. So that's an extension, but the geometric interpretation of that extension is that we're pulling back along this cover. And this cover is, am I saying it right? It's just, tensoring with the Eisenstein field. Tensoring with the spectrum. Well, it's geometrically Cartesian product with the spectrum of the Eisenstein field or something like that. So the top here is the pulled back thing, and the bottom is the thing that I want to get the pulled back thing to be. So I'm trying to check and make sure that they really are are equivalent. And if they're not, then I need to go back and put some extra relators in and put them in, before we pulled back along before we pulled back to get the cover.
Okay. Okay. Right.
I hope I'm not screwing up here by right. I mean, there's multiple covers going on here. I hope I'm not
Yeah, that's why I was
simply
getting
ambiguous
confused,
about
but
which cover I'm talking about. Which cover or which covering I'm talking about.
yeah.
I mean, I'm pulling back a cover along a covering, or a covering along a covering, or something like that. So
So I mean, on the
Yeah.
bottom there,
yeah,
very, very bottom, you have this, there's a fact that helps you, which is that
yeah,
omega W cubed is equal to 1. That's why we have that automorphism.
yeah. I guess you're right. Okay, so you're reminding me that I economized over here by putting the dot there. I should have put that dot there in it as well.
Right.
Okay, so it's just that I and W have their usual characteristic properties.
Right.
And okay, and now you're alluding to the fact that the characteristic property of W implies that W cubed is 1, which yes, that right. Okay, yes, that helps. It helps in pointing out what I forgot to write down. Yes.
So what similar looking automorphism are you aiming to get?
Yeah, that's a great question. I thought it was completely obvious, and then
well, it's something like A plus BW goes to W times A plus BW.
Oh, okay. That might help. Let me see what you're saying. So
I would just try to draw a little arrow up on top that mimics what you had down below.
Well, but let me try to act out what you're talking about, and a little bit more room to write here. I mean, yes, okay. And let me just go back for a second and maybe do what you said, which is just kind of. I just want to put this arrow here and
right.
say that we're trying to figure out what it would be. But now it sounds like you're saying that A plus BW should go to, don't tell me. Don't tell me. So let's see. You can probably do this way faster than I can. Let's see. Okay. So first of all, if I just multiply A plus BW times W, then what do I get? And it doesn't even matter whether it's formal or actual at this point. I mean, right? How does this work? It's like AW plus BW squared equals AW plus B times -1 minus W equals don't tell me, negative B plus A minus B times W.
Yeah.
Okay, so it sounds like you're saying that that this is going to negative B plus A minus B . So maybe you're right. Okay, yeah, right. So on downstairs we sent X somewhere, and it was X directly multiplied by this W, but now we're sending A and B somewhere, but it has to be in this way that formally involves W. So it's, yeah, okay. So it sounds like you're saying that A goes to negative B and B goes to A minus B. Is that what you're saying?
I guess so, yep. So up above, you can sort of hope, we're hoping that there is an automorphism of that algebra that does that.
Oh, and maybe you're hinting,
maybe there's not.
but it sounds like you're hinting that that might give us a guide to putting in extra relators that we might be missing.
Right, yeah, so that like we want to put in just enough to make sure that is an automorphism.
Yeah, it's quite possible that that might help, but let's see. So we have A goes to, what is it, negative B, and did I say it backwards? A goes to negative B and B goes to A minus B. Something like that.
Yep.
And all right. And we really are trying to wrap up here by 1 p.m., which means in the next 5 minutes. And that's perfectly okay, because this is just, helping me to organize. Like I say, I'm just trying to get you to help me to figure this out. And I'm still struggling with it at this point. But I think I'm getting hints about how to do this. And then, next time I come back and I tell you the much better story after I get this making sense. So
I'm gonna venture yes, which is that, so you had this quoted relation, A plus BW cubed equals K.
Yeah.
And so I think what you want, but don't have, is the same type of quoted relation where you've now done this transform where A goes to negative B and B goes to A minus B. So if you just take that quoted text.
Well, that's interesting. It seems like a bit of a wild guess, but maybe a good wild guess.
Well, it seems like you need that quoted relation that modified quoted relation to hold for there to be an automorphism that sends A to negative B and B to A minus
well, okay,
B.
so maybe wild guess wasn't quite the right word, but
not wild for me.
Cubed
just a guess.
Equals K. I mean, that's certainly different from what I was thinking. Well, okay, I just got 2 or 3 minutes left here. Let me just, okay. So I found your contribution helpful, and right. Again, I always just say things are lowbrow or highbrow, and then I change my mind about which is which. But right, this seems helpful in a sort of lowbrow way, but let me try to say my vague ideas about how I was going to try to figure this out by allegedly more highbrow way, and then I'll just quit here. So what am I trying to say? That well, on good days I understand, this whole synthetic differential geometry idea, which is, Lovier's take on Grothendieck's exploitation of nilpotent elements to make infinitesimal calculus make sense in algebraic geometry. Now, maybe that's way too modernistic. Maybe this idea I guess this idea actually goes back to Leibniz, but it's just I'm invoking Lovier and Grothendieck, maybe because they helped people like me understand it. But yeah, I think the idea is sort of, in some sense, to really go back to Leibniz or something like that. I think Lovier always claimed that they did. Except I can't remember whether Lovier, hated Leibniz and liked Newton or vice versa or what, or I don't know. Maybe he liked both of them. So let's see. So what am I trying to say here? That well, are you at all perceiving this analogy that I'm claiming between what we're doing here with this formal treatment of W and synthetic differential geometry, where there's this formal treatment of the infinitesimal, I guess we call it T, so I call it T sometimes, and there's like an infinitesimal time or something like that. So what am I trying to say? So that there's right, if we have k t mod out by t squared equals 0. So that's sort of the basic idea of, you know, Leibniz's calculus and synthetic for differential geometry and Grothendieck's nilpotent infinitesimals and everything like that. And so what's going on here? There's like, let's call this A. And then we have, just temporarily, we have like A modules, and we have K modules, and we have some adjoint functors going on here. And A, so what do? You take K modules and you like tensor with A. And then this may have actually worked out. I think I do want a right. I wrote it on the right, but I think I really do want the right adjoint. Is that right? I'll put a question mark there. But that, right? I mean, so the geometric interpretation of this tensor product here is that we're taking a bundle and we're getting a trivial, no, we're taking a space and getting a trivial bundle from it by, you know, the fibers of the trivial bundle will be the old things. The old, you know, the inputs become the fibers of the new thing. And then the adjoint to that should be like taking the sections or something like that. And you get the tangent bundle by first taking the trivial bundle and then taking this. So it's like the monad of this adjunction. Is it a monad or a comonad? Maybe it's a monad. You know what I'm saying? It's like, so I mean, right. There's this idea of that the tangent bundle of X is X to the D, where D is this infinitesimal space or something like that. But that's actually that's a composite of adjoints. That first you're taking X cross D, and then you're taking the sections of this bundle of X cross D projecting down to D. So you see what I'm saying? X cross X to the power of D is the sections of this thing. So I don't know. I'll start to leave it there right now. But there's sort of like this bundle discipline, the discipline of how to work with bundles and distinguish between sections versus total spaces and trivial bundles, and combine sections versus sections as like the right adjoint, and total space is like the left adjoint. Maybe I got it backwards, but there are these left and right adjoints to taking the trivial bundle. And then you can compose these adjoints together and you get all sorts of stuff. And if I conceptually clarify these in my mind, then do this in the analogous case where the exponent D is not going to be the walking tangent vector, but instead it's going to be the Eisenstein spectrum. If I clarify that all in my mind, then I'm hoping that this will give me a highbrow picture of how to repair my calculations, which hopefully will mesh with all the other lowbrow ways to repair this calculation. So like your lowbrow way and my lowbrow way involving my mathematical calculations or anything like that. So
yeah.
But the basic message is that I have to go home and think about this and try to get the calculations to work before I can give you a better story about this. So thanks a lot. And I'll see you next time, hopefully.
Yep. Next time I won't be late, I hope.
Right, but it was actually right. Every time you're right, that won't work if we try to So every time you're late, it helps me.
So if you know ahead of time that I'm going to be late.
Yeah, it has to be an unexpected. So be unexpectedly late next time.
I could do it like 1 hour later every time, but that's probably not so good for me, actually. Although for you, it might be great, but.
Oh, that's true, but I'm not sure that's for the same reason. But anyway, I'll think about this. Okay. I'll see you.
Yeah, see you.
Bye.
Bye.